Hello again. We're about to talk about a topic that will look kind of scary when we start looking at the equations, but the idea is simple. So if your equation's kind of scary, you just kind of go back to this idea, and the idea is this statement right here. The total pressure of mixture of gases equals the sum of the pressure that each gas would exert if it were present alone. In other words, all the pressures are the individual pressures contributed by each type of gas molecule just adds up. They just add up to the sum of the pressure inside of the container. Well, this actually gets us to what we call Dalton's law of partial pressures. And so this law of partial pressures is all it says is that the P totals, notice we're using subscript total just to kind of indicate that it's all the pressures, okay, will equal to P1 plus P2. So imagine you have a mixture, say, of oxygen, O2 plus nitrogen, and indeed you do, N2, because you're breathing right now. But this mixture right here, right, is atmospheric gases, two of the most plentiful atmospheric gases. It just means that the sum of all the pressure of the atmosphere is just due to the pressure contributed from oxygen plus the pressure contributed from nitrogen. Well, recall from the ideal gas law that if we have PV equals nRT, that we can solve this for pressure, and it just becomes P is equal to nRT over V. That means that this pressure would be equal to, or this pressure total would be equal to the oxygen and nitrogen pressure, but the number of moles of nitrogen, number of moles of oxygen will most likely be different. They are in our atmosphere. But the ideal gas constants obviously is the same from the individual ones. So if we say have P of O2, this would be N of O2, but R is the same. The temperature is the same because the gases are mixed together and in thermal contact. And the volume is the same because they're in the same container. It's one mixture, right? And so this essentially just becomes PO2 is equal to NO2 with these being isolated outside because these are all the same. Um, and then the pressure total, we'll look at an equation for that. And so this is the equation where we have the pressure total is equal just to the sum of all the moles times the ideal gas constant. I did not mean to mark that right there. Ideal gas constant plus the temperature, or times the temperature over the volume. And so it's just equal to the number of moles total. Well, this equation allows us to actually answer many different useful questions. Say you're doing a reaction in the gas phase and you want to know what percent, what percent in moles each one of these are, and you want to know what the pressure is contributed by a particular type of gas. Well, this equation or this idea will allow you to do that. One other thing about this, and this is also something from lab, let me go ahead and move myself there. Look at that. That because of these partial pressures, you have to actually be concerned about the type of reactions and where you're having reactions go. Because if you have any liquid, and virtually any liquid, anything that has even appreciable what's called vapor pressure, where some amount of the molecules in the liquid are going into the gas phase, getting just enough energy to go from liquid phase to gas phase, then we actually have to do some interesting mathematics to figure out the pressure contributed by a gas, say if it was generated, reacted, and bubbled through water. So the pressure of the gas, and we did again use this in lab, the pressure of the gas, which we were looking at, which was of course pressure for CO2, would be equal to the pressure total, not totat, minus the pressure from the water, because whenever you have a little pocket of or an opening above a liquid water, some amount of that water is going to go into the gas phase. Just a couple of molecules in there would just get just enough energy to escape from all their little water brethren and run off. So there's one more idea that we want to look at, which is mole fraction. But before we get to that, I want to look at just an example of using this partial pressure law. So Imagine we have a gaseous mixture made up of 6.00 grams of O2 and 9.00 grams of CH4. This is methane. And it's placed in a 15-liter beaker vessel at 0 degrees Celsius. This would have to be a closed vessel, so a beaker wouldn't work so well. Let's say 15-liter sealed drum, pressure container. What is the partial pressure of each gas, and what is the total pressure in the vessel? So in order to do this, this is actually just the same type of calculations you guys have done before. There are just a couple more of them. Okay, so we would convert each one of these masses into moles. So if we take 6.00 grams of O2, convert that into moles, of course it's 32.00 grams for every 1 mole. And if we take the 9.00 grams of CH4 times its inverse molar mass, 1 mole is it'd be 12.01 plus 4.04, which would be, I think, 16.05. 4.04. Yeah. Just putting that in my calculator. It was a long night. 16.05. There we go. So we get this. We got 6 divided by 32 is 0.1875. Don't have that many sig figs, but I'm going to keep that other one just to not have as much rounding error. And 9 divided by 16.05 would be 0.5607. Again, just keeping one extra. This, of course, would be moles of O2, and this one would be moles of CH4. The second part is to use the ideal gas equation to calculate the partial pressure of each gas. So if we do that, right, we would have the pressure and temperature and so on and so forth, but we start with PV equals nRT, and then we're going to solve it for P. So P, let's say no, not CO2, P of O2 would be equal to the number of moles of O2, so 0.1875 times the ideal gas constant, actually let me put mole, times the ideal gas constant, 0.08206 liters atmospheres per mole Kelvin. And then we would do times the temperature. So if we're at 0 degrees Celsius, to convert that to Kelvin, we add plus 273. So that'd just be 273. And then we divide by the volume in liters. Luckily, it's already given in liters in this problem. So here we go. Doing the calculation, we'd have 0.01875. 0.1875, not 0, times 0.08206 times 273 divided by 15, and we get a value of 0.280. I will go to the correct number of sig figs at this point. That is our value. Notice we have moles canceling, Kelvin canceling, liters, where does the liters cancel? Liters cancel here and here. So we have all of those guys canceling, and we end up in units of atmospheres. So that's the atmospheres from O2. To do the calculation for the atmospheres from methane, we just replace this value with the moles of methane, and everything else is the same. So instead, we have for CH4, put P for CH4, we would have the 0.5607 times 0.08206 times 273 divided by 15, and we get a value of 0.837 down to 3 sig figs, and that would be atmospheres of methane. Of course, the total pressure of this is just the sum of the two pressures. Remember, P total is equal to P1 plus P2. And so we would just have 0.837 plus 0.280. So 0.280 plus 0.837 is it says 117. Oh, that actually would go down to that many atmospheres. So remember the addition subtraction rule. We have data all the way down to the thousandth place and data all the way down to the thousandth place, so we can record to the thousandth place. So that gives us a value. Just that little last thing about the mole fractions. This is a really useful idea. If you have a ratio of the pressure for a particular gas, say in our last example, we have the pressure for O2 over the pressure for total. That ratio of pressure of O2 over pressure total would be the same as the ratio of the moles of O2 over the moles total, which is nice. These little mole fractions essentially give us the same value. Remember that this works out because, remember when we said the pressure for a particular gas would be equal to nRT over V? Well, if we got a mixture of gases, the only thing that's different is the N. And so if we have pressure 1 over pressure 2, the only difference would be N1 over N2, because R and T and V would cancel in this side of the equation, right? RT over V over RT over V, all that cancels down, just becomes 1. So those mole fractions allow us to do certain things. And then just a kind of nice, interesting fact, the mole fraction of air in our atmosphere is about 0.78%. So if you're looking at a barometer and 760 torr, then the partial pressure of nitrogen, the pressure contributed from nitrogen would be 0.78. Remember, converting it into a decimal, times the total pressure. We got 760, and so it would be 593. Really should only have 2 sig figs, so let's say 590 torr of the atmosphere is contributed by nitrogen. The other stuff is from the oxygen and the water and the little bit of argon. There's a little bit of argon in there and a few other things in trace amounts, CO2 and so on and so forth. So this is partial pressure. So there are a couple of questions on Chem 101. These guys will be a little bit trickier, so make sure that you have a little bit of time tomorrow during some of the conferences in case you do have questions. Some of them you gotta kind of think through, maybe use some of those mole fractions, or the ratios of pressure over pressure would be the same as the ratio of moles over moles. Those guys are really useful ideas. But again, we're in chapter 11. Go look for chapter 11, problem set 4, and I will talk to you tomorrow.